welcome back to Online Statistics. Today we will be talking about one of my favorite topics, randomization. Randomization is really cool because it's a statistic that's different than many others. It's relatively new, and in fact there aren't many statistics programs that run randomization tests yet. So I'm going to give you a tool on how to do randomization by hand, which is tedious and you would not have fun doing it. And then I'll show you how to do a randomization test in Excel, and I'm going to explain the logic behind this randomization test. We'll talk about assumptions a little bit, assumptions of past tests, and how randomization kind of fixes the problem of not meeting those assumptions or violating assumptions. We'll talk about the comparison distribution and where it comes from with the test of randomization. And then we'll actually go through an example of randomization testing so that you can see how you calculate the test statistic in randomization. I think randomization is really intuitive, easy to understand. This is the test statistic that I taught my son. So when he was doing his project on video games, wanting to know if there's a difference in playing video games or not playing video games and your improvement or your score on this math exam. So let's talk a little bit about assumptions. Now, with past assumptions, with the t-test, with all of the t-tests, you have the assumption of normality. With ANOVA, you have the assumption of normality. And today, with randomization, if you had violated that assumption, so say you look at the data, your sample data, and it's completely not normal. It's skewed, it doesn't look normal, and you go, whoa, this probably didn't come from a population that was normal, and you don't have a large enough sample, to overcome that, then what do you do? So here's a great tool. You can use randomization because it's not based on the theoretical distribution, the normal distribution of the means, the sample means. Remember, the t-distribution is based on those sample means. If you sampled over and over and over and over from a normal distributed population, randomization is based on a distribution that we create ourselves. We create it from the sample data. And so you don't have to meet these assumptions. So this is a great tool to use either when you violate the assumptions or if you just want a simple statistic that you can use this with, even if you meet the assumptions. So say you have normal data, randomization works well for that too. But it is a great tool when you do violate those assumptions and you can't use the statistics that normally come in your stats packages. All right, so the comparison distribution from the randomization tests, instead of being based on a theoretical distribution, based on the theory, now you've seen where the t distribution comes from, where the f distribution comes from, you've seen where the chi-square distribution comes from, our distribution we converted to t, so you should know all of those distributions come from a mathematical calculation based on the idea of sampling over and over and over from a certain population, probability, it's creating those different curves, the different distributions. Now this is not based on a theoretical distribution that's calculated mathematically, but instead it's creating a distribution from the data that you gather from your sample. So you take this data and you generate a distribution based on the data you already have. So if the data looks a certain way, then that's the distribution you're going to be comparing it to. And so the comparison distribution here is created by the researcher. And so you don't have to meet those underlying assumptions. All right. I'm going to give you an example of a randomization test using a question about administering GABA so GABA, if you haven't taken a psychology class or a biology class where you've learned about GABA, GABA is a neurotransmitter. It's in all of your brains. Hopefully it's working right now. It's an inhibitory neurotransmitter in the brain. So it opens chloride channels, it inhibits neurons. And so we're going to ask a question here. If you administer GABA, if you give GABA to lobsters, will it decrease their heart rate? Right? Now, we might expect their heart rate to be decreased because GABA is inhibitory. It opens chloride channels with chloride's negative, so it inhibits the cells. So you might expect it to have an inhibitory effect on the heart. And so here we're going to administer GABA to some lobsters, and then other lobsters will be our control group. They don't get GABA. They'll get an injection, but it's not going to be an injection of GABA. It'll be saline or some control that doesn't have the drug that we're concerned with here. Now, suppose that we take these lobsters and we measure their heart rates, all of the lobsters who got GABA and the heart rates of all the lobsters who were in the control condition. And you end up with a graph that looks like this. The graph here this graph is showing you that on average, if you average the control group, the average heart rate was higher than the average heart rate for the GABA group. But you should know by now, you don't just go jump to the conclusion that, yep, GABA decreases heart rate, because we know that you might end up with a small difference just by chance. And so you can't draw conclusions about entire population and go, yes, GABA decreases heart rate in lobsters just based on this one sample. You have to go, how likely would it be to get this big of a difference by chance? If it's not very likely, then you go on with your conclusion of rejecting the null and deciding that GABA decreases, that there is a true difference in the population between these groups. Now let's think of the other things that could cause a difference between these two groups. Now hopefully you would have randomly assigned the two groups of lobsters so that you don't end up with all your big lobsters in one group or small healthy lobsters in the other group. Hopefully you end up with by randomly assigning to these two groups, pretty equal groups, not all the fast hearts in one group and slower hearts in the other one to begin with. But even when you randomly assign to groups, you might end up just by chance with a group of lobsters that has a higher heart rate than the other lobsters. So we're trying to decide, is this difference that we observed in this data set, is it a difference that's just due to chance, or is it a true difference due to the treatment, due to GABA? So you could think about my example I gave you when we started learning about t-tests. My son wanted to know, is it a true difference in math scores that he observed, or was it a difference just due to chance, not a difference due to playing video games or not? So both of these are good examples to use. This is similar to a two-sample t-test or an independent sample t-test, except we are not going to use the same methods for the t-test. Instead, we're going to take all of those values in those groups, and you could do this by hand. You could write them all down on pieces of paper. Write down all of the control numbers in red, write down all of the heart rates for the GABA numbers in black, and we're going to shuffle those numbers and create two equal groups, just like the GABA and control started off in two equal groups. But now these two equal groups are not only going to have lobsters who got GABA or control lobsters, they're going to be a mix of the two. And then we're going to divide them into equal groups, plot all those values, take the average, and calculate the difference between those two groups. We're going to see this new difference between the groups when you randomly shuffle is a difference not due to treatment, because now the group's all mixed up, but just a difference due to chance, which lobsters ended up in which group. So you do this over and over and over and over. And the theory behind randomization is that if you do this over and over and over and over, and you see a big difference that's similar to what you started off with when they were separated by the treatment, by getting GABA or not, if you see that big of a difference or bigger over and over and over, then just by chance, then probably this difference you observed is likely to happen by chance. If you don't observe a very big difference compared to what you observed at the beginning, when you shuffle over and over and over and over and over, then that, not observing that big of a difference means that by chance you probably wouldn't get that big of a difference observed, so it's probably due to the treatment. So here, if you look at the difference, the GABA group had a mean of 14.5, and the control group, the group that didn't get GABA, had a mean of 19.7, which is a 5.2 difference between the two groups. So this is what we call our observed difference. You want to keep this difference in mind, because this is really important when you calculate the test statistic that we use with randomization. So go ahead and write down 5.2. You're going to want to keep that in mind. I'm going to put it on my calculator so I don't forget it. 5.2. Now is that a big difference? Is it a small difference? Would you get that big of a difference by chance? That's what we're going to test by shuffling these scores. So we're going to shuffle the scores over here in the control group with the scores over here in the GABA group. We're going to mix them all up, create two equal groups, and see how big that random difference is. And if the difference is less than 5.2, then we go, oh, by chance you probably wouldn't get that big of a difference. If we get a difference of 6, a difference of 7, by randomly shuffling these two groups, then you know that it's not very likely that difference reflects a true difference due to treatment. It's probably just a difference due to random differences or chance. So let's pretend we shuffled these and we came up with two groups. Now I did them in different colors just so that you know that the red originally was GABA, the black originally was control. Now we call this group, the first group, control, because we were comparing two groups. You could call one control and one GABA, but it's no longer a control and GABA. These are just random splittings of the groups. So the first group, the control group, now has a mean of, now I put in a control group because it's not a true control group. It's a group that's mixed of GABA and control. It's a random group that we're going to call control. And now this average is 19.5. The GABA group, it's not really a GABA group, it's just a random shuffled group, has a mean of 18.3. So now we subtract those to find the difference. The difference between those two groups is 1.2. So 1.2, how does that compare to our observed difference? Is that bigger or smaller than what we observed when they were broken up by condition, by getting GABA or not? So 1.2 compared to 5.2 is smaller. There's less of a difference just by random, but we only did it one time. You know that our distributions that we've used in the past are based on doing a sampling over and over and over and over and over and over and over. So that's what we're going to do with randomization. We're going to do it again. So we throw them all back if you're using flashcards, just like you did before when I had you shuffle flashcards to learn about standard error. But this time, instead of doing it to learn about a distribution, you're doing it to create a distribution to compare your test statistic to. So you're going to shuffle again. We throw them all together, shuffle, and create two groups. And this next time, we only end up with the difference between the means of these two randomly shuffled groups of 0.1. So once again, the difference was not as big as our observed difference of 5.2. So you would do this again and again and again and again. And ideally, you would do this several times. Here's again. Now, you might end up with all of the opposite in all of the control in the GABA group and all of the GABA in the control group, which would give you a difference of 5.2, but it'd be the opposite difference of 5.2. But it's not likely to happen over and over and over this big of a difference by chance unless the difference you observed at the beginning was only by chance, not a true difference. So you shuffle over and over and over, just like I was shuffling, shuffle, shuffle, shuffle. You're going to keep shuffling. And eventually, you come up with a set of differences, random differences. So you might do this 100 times or 1,000 times or 10,000 times, and you come up with a number of differences between the groups that's just random. And then you're going to take, this shows the distribution of those differences. As you see, most of the time, the distribution of these differences was around 0. So here's the frequency of the distribution. So here's frequency over here on the y-axis, and difference between our randomly shuffled groups over here on the x-axis. Now these differences, remember, these just come from randomly putting them in two different groups. Most of the time, the difference between those groups was 0. Okay, you see here. And as you get further up, higher and higher, or further down, lower and lower, negative would just be the opposite group being higher than the second group being higher than the first group. And so you have fewer and fewer observances. So based on our data, we created this distribution. Does this look familiar to you? It almost looks like the normal curve, doesn't it? So we created this distribution of random differences if you sampled over and over and over using our own data set. Now it may change shapes depending on what your sample distribution looks like, depending on the differences between those two groups that are random differences that you would find from sampling over and over and over. But the key here is that we want to compare our test statistic to this distribution that we've created. You want to compare the test statistic to this to see how likely it would be to get the observed difference of 5.2. So what you would do is on this distribution, you would plot your difference that you observed in your test statistic, 5.2, which is going to be way up here on this end, and you would calculate the area that is that extreme or more extreme in order to determine whether it's probable that this happened by chance or not. If your test statistic was in here, at maybe 1, right in here, then you would have a lot of area, a lot of observances beyond that happened just by chance, by random shuffling. If your observed test statistic, the difference between your two groups was 0.2 right here, then you'd have a lot of area or observances calculated that happened just by chance. And so you would retain the null, decide that there wasn't a true difference between the groups, that the only difference was due to random shuffling, perhaps. And so if your test statistic falls within the center, the middle part of this, close to 0, you are going to retain the null. If it's far off on the ends of this distribution you've created, then you reject the null. Now let's look at calculating the actual numbers for making your decision in a randomization test. So you remember alpha, the 0.05 or 0.01? If you have an alpha of 0.05, then you're going to have to calculate some numbers. So far we've only looked at theory distributions, but you're going to have to calculate numbers so that you can decide, do you reject the null or retain the null? Now, in a randomization test, what you are going to calculate is a p-value. You're going to calculate a p-value. And if you remember from the past, if your p-value is less than alpha, you reject the null. If your p-value is greater than alpha, you retain the null. And that's because your p-value represents the likelihood you would get that extreme of a test statistic just by chance. So the smaller p gets, the less likely you would get that test statistic by chance. It's the area beyond your test statistic. Back in the t-tests, it was the area beyond your test statistic on the t-curve. Now it's going to be the area beyond our test statistic on our created distribution from the random reshufflings. Okay. So the way that you calculate p is you're going to take the number of times your random differences. So when you randomly shuffle over and over and over, the number of times those differences equaled or exceeded your observed difference. Okay? And then you're going to add 1. I'll explain why in a second. And you divide by the number of random regroupings that you did. So if you had 100 random regroupings and only 2 of those were equal or greater to 5.2, then you would do 2 plus 1 divided by 100 plus 1. So go ahead and try this. 2 plus 1 divided by 100 plus 1 would be 3 divided by 2 plus 1 is 3 divided by 101 equals p is 0.02. So 0.029. So if you had a 0.05 alpha, you would reject the null in that case. And you would decide that the observed difference is not likely to happen just due to chance. It's the number of times you rejected or the number of times you exceeded the observed difference was not enough to retain the null. So let me give you an example here. Let's go ahead and I'm going to write some on the board over here. And let me give you an example. Let's say that we started off with a difference. So your observed difference, sometimes this is called OTS. Your observed difference was 5.2. This is the difference between the two groups. And we're asking, is that difference just due to random shuffling, or is it due to true differences between getting GABA or not? And so let's say we shuffled again, and we got 0.1. And we shuffled again, and we calculated the difference between the two groups, and you get 1.2. And then you shuffle again, and you get 5.7. And you shuffle again, and you get 2.2. And you shuffle again, and you calculate the means for each of those groups. You subtract the mean from one group from the other, and you get a difference of 2.3. And then you do this again and again and again and again. Now, let's say we do this 100 times. So we shuffle 100 times. Shuffle 100 times, which you see could be tedious if you have cards and you're shuffling over and over and over. But then you go through and you count how many times your random differences, remember these are just random differences from shuffling over and over and over. You're going to look at this random difference. Did it exceed your observed difference? You go no, so you don't count that for your test statistic. Did this one exceed your observed difference? No. Did this random difference? Yes, this one exceeded your observed difference. So you're going to count 1. Then you go, this one, nope, this one, no. Say you have another one, 6.0. Yes, that's 2. So you're going to tally up how many out of this 100 times was greater than 5.2. So giving evidence towards the null hypothesis that you could get that big of a difference just due to random shuffling. So you count them up. Let's say that we counted up out of the 100, I don't have all 100 on here, but let's say out of the 100, we counted up 17 different times that we got 5.2 or greater. Okay, 17 different times. Now to calculate P, you're going to have 17 as the number of times you exceeded, so 7 exceeded this 5.2, equaled or exceeded it, divided by the total number of times you shuffled, 100, plus 1 on each of these. Now the reason I tell you why we add this plus 1, the reason we add the plus 1 is because you start off with a group. You started off counting the mean for the group that got GABA and the mean who didn't for the control group. Now that could be a random difference. Okay? So we count that in the plus 1 because there was one time we observed 5.2 at the beginning. That was our observed difference. And we count that as a shuffle in the bottom. So one time we observed that big of a difference to begin with. We start off with that, adding that 1, and then the 100 times we count those as additional times. So the 17 were out of the random differences. So you'd add 17 plus 1 is 18 divided by 101. And you end up here with a p-value of 0.178. So you would say p equals 0.178. So what do you decide based on this p-value? Now, if your alpha is 0.05, your p-value is above alpha. So you can draw this out. You could draw this out as a distribution. You could go, okay, your alpha's 5% or 0.05, and your p-value, the area beyond your test statistic, is greater than that. So your test statistic is probably right here. Your test statistic random reshuffling leaves 17.8% on this curve. Okay? Now remember, I just drew the normal curve because that's what we came up with our random differences. We're not using the theoretical normal curve. You could have a different shape of this curve. But here, the key is that if your p-value is greater than 0.05 or your alpha value, then you retain the null. You go, it's probably likely that we observed this difference just by chance, this 5.2 difference just by chance. You retain the null. You say there isn't a difference between the two groups. If the p-value is less than 0.05, you reject the null. And if it's less than 0.05, that means you didn't have many observances by chance because this number was small. The numerator was small compared to the denominator. You didn't have very many observances by chance that were greater than, equal to or greater than the observed difference when the groups were separated by the treatment. And so there's not very much evidence you would find that big of a difference just by chance. So you reject the null. You decide, yes, the two groups are truly different. And that's what you go with. There's not a lot of chance or high probability you would get that difference just by chance. Okay, so now I'm going to show you how to use Excel to calculate randomization. Let me pull up Excel. Here I have 10 IQs. So over here I typed in 10 different IQs. For infants who listen to music before they were born. Some people think that listening to classical music helps develop the brain. And so I made up these IQs, so don't take the results of this too seriously. But I have 10 IQs from individuals or babies who listen to music prenatally, and then others who didn't listen to the classical music. They were randomly assigned. The parents played the classical music near their belly when they were gestating, and they then later, when the child was older, brought him in for an IQ test, or so the story goes. And so we have these different IQs. Now you know how to, with Excel, hopefully calculate a formula. So I'm going to just put here equals, and we'll get the mean. Remember, you can use this formula function. So I'm going to go average, and I'm going to first calculate the average of the children who listen to music. So here I have the mean music group, and I'll calculate right here, no music, and we'll put this equals the average. So just like before, you can go up to the shortcut bar and click average here, and now you want to select all of the no music. Oops, I missed one. Select all of the no music kids there, and you should know how to do this from the last video I showed you. So it looks like the kids who listened to music had an average IQ of 100.7, and the kids who didn't listen to music had an average IQ of 97.4. Now we have to ask, is that difference big enough to reject the null and conclude that there really is a difference of IQ based on listening to music or not? Or is it just a random difference and we should retain the null that there is no difference in these populations? So what I'm going to do is I'm going to take the difference between this first group. So if you click on this and put equals, and you can do the first group minus, so I click the minus sign there and click on the second group. So now it has a formula in this cell to take D11 minus D13, to take this mean and subtract the second mean. So you want to set up these formulas when you do this. That way, when you rearrange and change this, it'll calculate the difference for you. So right now, I'm just going to put in observed difference. It was 3.3. Oops, sorry. 3.3 so that we can remember that, because this is going to change when we shuffle and deal the scores again to two random groups over and over and over. So now what you would want to do, you know that our observed difference was 3.3. We want to randomly shuffle these numbers, and Excel has a great way to randomly shuffle numbers. I just typed in random numbers there, but in order to create a random number between 0 and 1, you can type in equals. So go ahead and do this, equals, and then go to this formula function, and you might have to put all here, and then go down to our random, R-A-N-D, and it tells you here returns a random number greater than or equal to 0 and less than 1. So you can, I click OK, and there you go, types in a random number. Now I'm just going to copy this into all of these cells. You can either drag it, or you can click Control-C, Control-V and copy it, or copy and paste. But in Excel, if you highlight this little square here, you can drag it down and copy the formula. So these are all random numbers between 0 and 1. Now what I'm going to use this random list of numbers to do is to put these in a random order, to shuffle them in random order. So what I'll do is I'll go to Data and Sort, and your version might be a little bit different if you have a newer version of Excel, but I'm going to sort by random numbers in ascending order. And let's see, before I do this, you only want these three rows to be in, these three columns to be highlighted, because you don't want to randomly shuffle your music and no music, the difference calculations. So you want to highlight that, go to Data, Sort, and I'm going to sort by random numbers, click OK, and it should shuffle. So it shuffled. Now you can see this was a music, no music. So it shuffled these scores so that you have the first 10 up here, a random 10 now, and the second 10 are random. It's no longer just music and no music, but because in your cell here you said to average A2 through A11, the first 10, it's going to be averaging that random group now, and the second one's going to be random, taking the average of that second random group. And so now it calculates the difference between those two random groups. It's 2.1. You can just type it or write it down so that you remember it. 2.1. Now this is a random difference. So far, did that random shuffling support the null or support evidence against the null? So it was smaller than our observed difference. So you went, oh, maybe the observed difference, maybe there really is a difference between listening to music and not, that wouldn't be expected by random. But remember, that was only one shuffling. So you'd want to do this over and over and over. So you can just go up to Data again, go Data and Sort. Oops, I didn't select the correct data. Do Data, Sort, random numbers. So you sort it again. So now it has a new difference of 1.5. So you add that to your list, 1.5. And you're going to do this over and over and over. You essentially want to do this 100 times, and then you calculate. Now, if you only do it twice, here's a problem with only doing randomization tests twice, only shuffling twice. If you get one time and you add that exceeds the difference, and you take 1 plus 1 for the top of your p-value. 1 plus 1 equals 2 divided by the total number of shuffles, so there's only 2 plus 1, so 2 divided by 3, you end up with 0.66. You're retaining the null. You don't reject the null. What if so only one time. What if you end up with both times? So you see here where one time rejecting out of 2, 50% of the time you were rejecting, but or getting a random statistic greater than your observed statistic, but you still don't reject the null because there aren't enough times. It's based on a distribution of sampling over and over and over and over and over. So it's based on randomly redistributing your sample over and over and over and over. So you really need to do a randomization test several times. You would keep doing this, click randomization, but it's a whole lot easier to use Excel than it is to do this by hand on flashcards. You could have these numbers written down on flashcards, shuffle them, put them in 2 groups of 10, calculate the mean of each of those groups, calculate the difference, but that would take a long time. So Excel, you can click, 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 record those 100 values, then count up how many of those values exceeded this observed difference of 3.3. So far we have 0, so it'd be 0 plus 1 on the top so far of our p-value. And then you divide by the total number of shuffling. So if you did 100 times 100 plus 1 to calculate your p-value. If p is less than 0.05, you reject the null. If p is greater than 0.05, you retain the null. If you retain the null, you decide there is no difference in the population of IQ based on listening to music or not. If you reject the null, you decide, oh, there probably is a difference in the population. It's not likely we would have gotten that big of a difference just by chance. And you conclude that based on your reshuffling. So you're essentially creating chance yourself. So that's all I have for today. Randomization is really a fun tool that's intuitive. It's something you can teach to all your friends. And with a few minor modifications, you can do other tests similar to a one sample T or ANOVA. You can pretty much tweak it based on the logic to fit any test that you need to do, and it doesn't rely on all those assumptions. So this has been great. Today is our last lecture. So if you have any questions, please come to me, let me know. Hopefully you've learned quite a bit throughout the statistics course, and you've come to love statistics as much as I do. I suggest you go back and watch that video that we watched in the beginning of class, the stats rep video, and see how much more you recognize, how much more you understand compared to when you first came into this class. All right, it's been a fun adventure. Hope you guys have a great time.